Hello, Chemistry 12, Mr. Chan here. And today, what I want to do was introduce you to something brand new, and it's called chemical equilibrium. Now, what chemical equilibrium is that it will challenge you to sort of rethink of what you've learned about chemical reactions ever since you learned about chemistry or went in depth in chemistry back in grade 9. Now, up until probably the reaction rate unit, when we talked about chemical reactions, we talked about them being in open systems. Now, open systems are basically when the reactants and products are free to escape. And when we have an open system, what happens is the reactions are considered to go to completion. This was basically grade 11. Now, so whenever you did those single replacement, double replacement, synthesis decomposition reactions, you went from reactants and you got your products. And what would happen is you would represent your reaction with a single arrow. And basically, you said the reaction can only go in one direction. And so back in grade 11, when we were introducing you to the different types of reaction and stoichiometry, we assumed that the reaction went from reactants to products, and that is it. Now, when we talk about chemical equilibrium, we have to change how we think. Now we have to focus on something called a closed system. Now, what is a closed system? Another way to think of it is that it's like a sealed container. Now, when we have a closed system, what that means is the reaction is allowed to take place in a vessel such that neither reactants nor products are lost. Now, what happens is when we have these conditions, we get something called an equilibrium. These conditions result in an equilibrium in which you have constant visible properties, or what we call macroscopic properties, like temperature, pressure, color, due to a constant number of products and reactants. And the key other thing that you get in a closed system is we get the forward rate of the reaction from reactants to products is equal to the reverse rate, which is products going back to reactants. This is the key point that you should be aware of, is that the forward rate reactants going to products equals the reverse rate products going back to reactants. Now, one thing that you should be aware of is you will notice that when we deal with equilibrium, what happens is we use a double arrow. And what this double arrow does is that it indicates that the reactants can go to products and products can go back to reactants. Now, one thing about reactions at equilibrium is that it will physically or visually appear that nothing is happening, again, due to constant macroscopic properties. But in reality, the reverse and forward reactions are occurring at the same rate. So if I can just get my pen here, if I can, okay, so what you have here is the forward and reverse rates are occurring at the same rate. And since the reactions are continually occurring, the overall reaction is considered to be dynamic. So what do I mean by this? So what I have is I'm just going to share with you a simulation. So let's do this one. Okay. So back in grade 11, so what you have is you have your oxygen here, nitrogen here, and what you have is a sealed container. Now, back in grade 11, and recalling what you learned from reaction kinetics, what happens is these particles are moving and they hit with correct geometry and sufficient energy. And so what happens is you get a production of nitrogen monoxide. Now, back in grade 11 and even up to reaction kinetics this year, what happened was we assumed everything stopped. And what you would do is you would use your stoichiometry, your mole ratio, all that sort of stuff to calculate the amount of product produced, reactants used up, limiting factor, excess, all that sort of good stuff you learned from grade 11. But this in reality doesn't stop. This reaction does not stop. So in reality, what happens is the particles are continually colliding to form either the products or the product particles are colliding to form reactants. And so this collision, these collisions are continually occurring. And when they occur at the same rate, that is where equilibrium is being reestablished or being established. So in this case, you notice products are being formed, reactants are also being formed, but because they are formed at the same rate, what happens is the macroscopic or visual properties remain constant. So if I get my pens back, perfect. Okay, so if we were to highlight this paragraph, a few things. It will physically, visually appear that nothing is happening. But in reality, the reverse and forward reactions are occurring at the same rate. And because they are continually occurring, because the reactions are continually occurring at the same rate, this is said to be a dynamic equilibrium. It is constantly going. Okay? Now, so because the reaction is continually going, a couple of key things that occurs. Number one, some characteristics of equilibrium. The reaction concentrations do not have to equal the product concentration. The concentrations just have to remain constant. Okay? Since the reactants are being formed at a constant rate as the products, the overall concentrations do not change. And this is why we say physically or visually, nothing is occurring. Now, if the conditions change, the equilibrium rearranges itself or shifts until a new equilibrium is established. We'll touch more upon that next class, but be aware that since it's a dynamic equilibrium, the equilibrium or the rate at which the reactants and products are formed can change. Now, it doesn't matter if you start with all reactants or all products, equilibrium will be reached at that given temperature. Okay, now what I'm going to do is in the description below, I'm going to put down two links. I think they are here. Let's see. Come on. Okay, where they are going to be the equilibrium water demo. So I'm going to post these links down in the description. And what it is basically a demo that I've done in class or will do in class that sort of explains the concepts of what dynamic equilibrium is and how, and explain the reasons why the reactants do not have to equal the products. The concentrations have to remain constant, or it doesn't matter if you start with all reactants or products, equilibrium will be reached. So what I will do is I'll put the two links in the description box below. Now, one other thing is that the rate of decomposition or formation depends upon the mole ratio. Now, let's say, for example, here, you notice in this particular equation, I have 1x is in equilibrium with 1y. So notice in this case, the mole ratio is the same. So what does that mean? It means, therefore, the change in concentration is the same. Now, what I want you to do is focus on this particular graph that I have here. So notice in this particular case, I have a graph of the concentration of reactants versus time and the concentration of products from concentration versus time. Notice in this particular case, notice the change in concentration. Here is around 0.02. Here, not particularly accurate, but this is also 0.02. So why are these numbers the same? The change in concentration is because the mole ratio is the same. So the change in concentration is dependent upon the mole ratio. And since this is a 1-to-1 ratio, the change in concentration is also the same. Now, the other thing that you might want to notice in this particular graph is right here. Notice in this case, the reaction is at equilibrium. Why? Because the concentration of products and concentration of reactants are constant. Okay, notice they're not the same. Notice the reactants at equilibrium is around 0.06 and the product is at 0.02. But notice they are not changing in their concentrations. So therefore, that is considered a equilibrium situation. And it goes back into my notes up here. It says, if you take a look here, the reactants do not have to equal the products. The concentrations just have to remain constant. And that's what has been done here at this particular section highlighted in orange. Okay, so this particular section right here. Now, in this particular scenario, I've given you concentration versus time, but you can take a look at equilibrium by looking also at the rate. So there are two different ways to graph equilibrium graphs. One is amount versus time or rate versus time. Be aware of the differences in the graph, but also realize how the two graphs are related. Notice in this particular case, notice the reactants is in red. Notice what's happening to the reactant concentration. How does that relate to the forward rate? Going back to reaction kinetics. Remember, as the reactant concentration goes down, what happens is less effective collisions, the rate slows down. Conversely, notice the products, which is in blue. Notice the product concentration is going up. So what is happening to the reverse rate? And why is that? And the last one is in purple. You have the equilibrium. There's no change in the amounts. So why are the rates equal? So are you able to reconcile these two particular graphs, the amount versus time or rate versus time? And are you able to understand why the graphs are similar, but also the differences in the graphs? Okay, so do you understand why the reactants go down? What's happening to the forward rate? Do you understand why the products are going up and what's happening to the reverse rates? And why is it equal rates, but the reactants and products are not necessarily equal? Again, if you want to take a look, you can watch the water demo videos that is in the description below, and you can take a look at that, and that explains, how these are all related. Okay. Now, when we talk about equilibrium, there are a couple of things we have to consider. One of them is enthalpy and entropy. Now, enthalpy, you've been exposed to this back in grade 11, is the heat content, or delta H. All chemical reactions favor the side with lower potential energy. Therefore, reactions tend toward minimum enthalpy or lower energy. Now, here, what I've done is in this exothermic reaction, this was chemistry 11. What were the ways to recognize exothermic reaction? So when we take it into equilibrium, we are saying for exothermic reactions, the products are favored and the reactions tend to occur, or this is what we call spontaneous. Why is that? Is because what happens is if you take a look at the energy of the products here, this has less energy. So therefore, more stable. Okay. So in this case, I could say products have less energy and therefore more stable. Okay. So what happens is since the bonds have less energy, it's considered more stable. Now, an example would be physics. Physics, why does a ball fall down? Why does an egg roll off the table? And some of you will say, well, because of gravity. Duh, right? True. But why does it fall down? Is because you're going from a high energy, which is on the table, down to a low energy on the floor. So this is why eggs naturally roll off the table and fall onto the ground. You don't need to push it off the table. It will naturally go to a lower, go to the ground because it's lower energy. So it has potentially less energy. Same idea here in terms of bonds. So in this case, the bonds have less energy, therefore are considered more stable. Now, if we take a look at endothermic reactions, okay, recall from chemistry 11, what is endothermic reactions? Energy is absorbed. And so what you have is you have delta H is positive, or the energy term is in the reactants. The reactants are favored and the reactions tend not to occur, or called non-spontaneous. So in this particular case, if we take a look at the energy of the reactants, I'm going to put a star here. The reactants have less energy. Energy, therefore more stable. So for an endothermic reaction, what's happening is you're going from an area of low energy, more stability, to products having more energy, so more unstable. So again, if we were using the egg rolling off the table, that is a spontaneous reaction. Picking an egg up off the floor and putting it on the table because you're going from a state of low energy to a state of high energy, that is considered non-spontaneous. An egg will not naturally jump from the floor to the table. You actually have to physically pick it up, give it energy. And so that's considered non-spontaneous. Same idea here. If you talk about the energy of the reactants, they are lower energy, more stable compared to products. And so therefore, it's considered non-spontaneous. The endothermic reaction is considered non-spontaneous. All right. Another one we want to take a look at is called entropy or spontaneity. So what is entropy or spontaneity? What that is the amount of randomness or disorder in the system. All systems tend toward maximum entropy or maximum messiness. So if we were to take a look at entropy, if we were taking a look at randomness, notice solids would be considered low randomness. This is why they're solid. They have low energy. They don't move very much. Gases have high randomness because the particles in a gas are moving faster and they're moving quicker. Another way to take a look at entropy is by looking at the number of particles. If you have a low number of particles, you have low randomness. High number of particles, you have high randomness. An example would be like a high school. If you had a high school of maybe only 300 kids, the diversity of courses, the diversity of students would be very limited compared to a high school of, let's say, 3,000 kids. If you had 3,000 kids, you would have all walks of life, and you would have a wide variety of electives that you can take. So more randomness. Conversely, versus low randomness, like a small high school. Okay, now, and the other thing is, all system tends toward maximum entropy or maximum messiness. You could even take a look at your hair. In the morning, your hair is perfectly coiffed, perfectly gelled, everything. By the end of the day, it's a mess. Okay, so even just by random movement of your head, you can mess up your hair. That's the same idea where particles go to maximum messiness. Now, if we were to take a look at enthalpy and entropy, we can say that all chemical systems tend toward minimum enthalpy and maximum entropy. And the perfect example of this is, AKA, teenagers. Teenagers are the perfect example of minimum enthalpy and maximum entropy. Teenagers, when they come home, all they want to do is just bed rot, sit on the couch, sit in their beds, and, take a look at their phones and on screens. They don't want to do anything. And if we tell the kids to say, clean up their room, go exercise, they'll be like, oh, I don't want to do it. And maximum entropy. No offense, teenagers. Look at your rooms. Your rooms are a mess. Okay? No matter how much your parents try to yell at you, nag at you to clean up your room will naturally end up being messy. And when you have a messy room, all you do is just transfer the clothes from your bed to your chair when you need to sleep. And when you wake up in the morning, the pile of clothes goes from your chair to your bed when you are trying to study. So that is maximum messiness. So you folks, teenagers, are a perfect example of minimum enthalpy, or you want to be as low energy as possible and as messy as possible. Okay. Now, I just wanted to give you an example here. It says, for the following reaction, decide on the basis of entropy and enthalpy whether the reaction will go to completion, reach equilibrium, or not at all. Now, in this particular case, the first thing you identify is you notice this delta H. Okay, so if you take a look at this delta H, you notice that this is an exothermic reaction. Now, because it's an exothermic reaction, therefore, the products are favored. Why are the products favored? Because they are more stable. Okay. Now, that is for enthalpy. For entropy, you take a look, notice the products is aqueous gas. Compare that to solid liquid. So in this particular case, the products are more messy. Now, notice in this particular case, both for enthalpy and entropy, the products are favored. So I'm just going to write here, therefore favored. So in this particular case, since both favor products, therefore reaction goes to completion. Okay, so in this particular case, both favor the products, so the reaction goes to completion. All right, that means when we say the word completion, that means we're going to get lots of products before the system reaches equilibrium. Now, if they both favor the reactants, then we could say that the reaction is not spontaneous, or we could say we have lots of reactants and not very much products. And when we say when one favors the products, the other favors the reactants, then we could say that it has reached equilibrium where we have almost equal amounts of reactants and products. Okay, so that's one thing I wanted to highlight here is that when we say the word completion, or when we say non-spontaneous or not at all, that means we have lots of products or lots of reactants before the reaction reaches equilibrium. When we say the word reach equilibrium, at this point in time, we are just saying that there is an equal amount, a relatively equal amount of products and reactants. All right, so that is the introduction of equilibrium. And again, what I will do is I'll put the video links to the water demos in the description below. And hopefully this will clarify some of the questions that you might have had if you missed my class. All right, friends, thank you very much. Have a good day. Bye-bye.